Okay, so at this point, what we're going to do is introduce a bunch of properties of limits that will make it basically a lot easier to calculate limits. Okay, so calculating limits and showing that something is a limit, as you see, is kind of a pain, right? You have to do this. You have to do this. This game of given the epsilon, find the time. Show that given any epsilon, you can find the time. Find the time past which it works. But fortunately, there are a bunch of properties that make things a lot easier. Okay, so properties of the limit. Okay. So first one is going to be like this. Okay, suppose you have some sequences, a sub n and b sub n sequences. And let's say that a sub n goes to L and b sub n converges to M. Okay, so I haven't introduced this notation before, but when we write something like this is the same thing as the limit of a sub n as n goes to infinity is L. Okay, a sub n goes to L, b sub n goes to n. So if that happens, then one, a sub n plus b sub n, this sequence converges to the sum of the limits. Maybe I'll write it using normal limit notation. So limit of a sub n plus b sub n is L plus m. So what this is saying is that the limit of a sum of sequences equals the sum of their limits. Right? The limit of a sum is the sum of the limits. Number two, the limit of alpha times a sub n as n goes to infinity is just going to be alpha L. And the limit of a product, a sub n, b sub n, as n goes to infinity, is going to be the product of the limits. This is really useful. This is useful because, for example, you know that the limit as x approaches c of x is just c, right? You know that, right? As x approaches c, the limit of x is c, right? Now, if I use property 3, then that tells me that the limit of x times x, as x approaches c, is c times c. Right? And it also tells me that the limit of x times x times x, as x approaches c, is just c cubed. And it tells me everything, right? It tells me that the limit of x to the n as x approaches c is c to the n for any n in n. Right. So you don't have to do the epsilon. You don't have to do the epsilon game for this sort of thing. Right. You don't have to do the epsilon game. Also, if you add these guys, you can, the limit of, say, alpha x of n is going to be alpha c to the n as x approaches c. Like, as n goes to, what am I doing? What am I doing? Wait a second. Sorry, I've completely messed up. What am I doing? Sorry, this is not what I should be writing. I'm thinking about something else entirely. Sorry. Sorry. Let me just think. Sorry. All that was from function limits, not sequence limits. Sorry. Okay. In any case, these properties make it easier for you to calculate limits, right? So, if I say, the limit. So, for example, the limit as n goes to infinity of 1 over n squared plus 1 over n plus 3, right? You can say, well, that's just going to be the limit of each of those guys. 1 over n squared plus the limit of 1 over n plus the limit of 3, right? So it's just going to be 3. Right. So you can just, the point is that you can use this theorem to break the thing up into pieces, and then just look at each of the pieces. Okay. There's one warning though. Warning. The sequences have to be convergent. Okay, this theorem doesn't hold if you're talking about divergent sequences. Right, so non-examples. If I talk about this sequence and this sequence, let me see this one. Suppose I take, okay, here's one sequence, right? What's the limit of this sequence? 0. Okay. Here's another sequence. What's the limit of this sequence? Infinity. Okay. But if I look at the product, what's the limit of this sequence? 1. Right? The limit of this one is 0. The limit of this one is infinity. The limit of this one is 1. Okay. So, it doesn't really make sense, right? You can't say the limit of the product is the product of the limits, right? And the reason is that this is a divergent sequence. So you can't use the theorem on it. Okay. So it's not, you cannot say, this does not show that 0 times infinity is 1. Okay. I'll give another example. Is -1 to the n. What's the limit of this sequence? There is no limit. It's divergent, right? -1 to the n plus 1. What's the limit of this sequence? Again, it's divergent, right? But if I add them together, get -1 to the n plus -1 to the n plus 1. What's that?
0.
That's 0, right? So this limit actually exists. This one goes to 0. You have something divergent and something divergent, and you have 0. Okay. Again, the theorem doesn't apply. You can only apply the theorem if the limits both exist, right? If these limits both exist, then the limit of the sum is the sum of the limits, et cetera, et cetera. But if one of them is divergent or both of them are divergent, you end up with some sort of crazy, it's not so simple. So that's just a warning, right? For example, if I have this one and this one, right? This one goes to 0, this one goes to infinity. What about this? What about the product? Well, the product, this one goes to infinity also, right? So does that mean 0 times infinity is infinity, and 0 times infinity is 1, right? Again, you have to be careful. Okay. So anyway, just remember this theorem applies when the limits exist. Okay, but it's a useful theorem. Okay, so that's one nice property of limits. Okay. Okay. Here's another one. Let's say that you have 3 sequences: A sub n, B sub n, and C sub n, and you know that they are in some order, right? A sub n is always smaller than B sub n, and B sub n is always smaller than C sub n. Okay. So you got 3 sequences, right? You got one low sequence, you got one high sequence, and you have one guy in the middle. Okay. If the limit of the low guy equals the limit of the high guy, then the limit of B sub n exists and is L also. Okay, so this thing is called the squeeze theorem, or the pinching theorem. Okay, like this guy in the middle gets squeezed, and if the top guy and the bottom guy both tend to some number, then the guy in the middle has to have a limit and end up with that number too. Okay, so this is useful in establishing limits. So here's an example. So A sub n is the square root of 4 plus 1 over n quantity squared. Okay. Okay. Or maybe I should call it B sub n. I'll call it B sub n. Okay. Then you could notice that, look, this guy is trapped between the square root of 4 and the square root of 2 plus 2 over n plus 1 over n squared. Oops. 4 plus 4. Right? Because I take away the n squared, take away the 1 over n squared here. I add in, it gets smaller. If I add in something, it gets bigger. Right? Okay. Now this thing is 2, right? And this thing is the square root of 2 plus 1 over n quantity squared. So that's 2 plus 1 over n. Okay, so now here's a sequence that's underneath. Here's a sequence that's above, right? You have one sequence that's just 2, 2, 2, 2, 2, 2, 2, 2. You have the other sequence, 2 plus 1 over n, right? And you have this guy in the middle, right? You have this guy in the middle, so you know that this is 2. This one goes to 2, and so this one has to go to 2 also, right? This one is forced to go. There's a 2 by the squeeze thing. Okay, here's another example of using the squeeze theorem. If we let our sequence be 2 to the n over n factorial, I hope you know what factorial means, right? Factorial means n times n minus 1 times n minus 2 times dot dot dot, all the way down to 1. So, like, b sub 1 is 2 over 1, b sub 2 is 2 squared over 2 times 1, b sub 3 is 2 cubed over 3 times 2 times 1, b to the 4 is 2 to the 4 over 4 times 3 times 2 times 1, etc., etc. Okay, so observe b sub 2 is the same thing as b sub 1 times 2 over 2, right? Right, here, right? B sub 3 is b sub 2 times 2 over 3, right? B sub 4 is b sub 3 times 2 over 4, right? Etc., etc. B sub n is going to be b sub n minus 1 times 2 over n. So, so past n equals 4, b sub n is smaller than b sub n minus 1 times 1/2. Right? Because starting from this point, you multiply by a half, and then afterwards, it's always some number less than a half. Right? So starting at this point, you multiply by a half, and then after that, it's always less than a half. Okay. So what you see is that b to the n equals b3 times, so past n equals 4, b sub n is b3 times 1 over 2 to the n minus 3. Right? At b4, you get b3 times a half. Right? So let me write it over here. B3 is B4 is B3 times a half, right? B5 is B3 times, is smaller than B3 times a half squared, right? B5 is smaller than B3 times a half cubed. B7 is smaller than B3 times a half to the fourth, etc., etc. Right? Because every time you multiply by some number that's smaller than a half. Okay, so now we can use the squeeze theorem. We say, well, look, b sub n is smaller than b sub for n bigger than 4. B sub n is smaller than b3 times 1/2 to the n minus 3 and bigger than 0. Right? This is 0. This thing goes to 0. And so this thing must go to 0 also. So the limit of 2 to the n over n factorial is 0. Let's squeeze that. So even though the exponential function grows fast, the factorial grows faster. Any? Yeah. So you see how you use the squeeze theorem, I hope, right? You try to find something that you try to find something that's bigger than this guy and smaller than this guy, and that converges to something. Okay. Both of them converge to something, and you squeeze it, you trap it between. Okay. Okay. So, anybody? Any questions about this one? This last example maybe is a little bit too complicated, but I hope you got the previous example. I hope you got this example, right? This is maybe the simple example that shows you how to do the squeeze theorem. This last example is maybe, I think the importance of it is mainly for me to show you that the limit of this is 0. Okay, but I don't expect that you would actually come up with this argument. This argument is pretty clever. Okay, so let's go back to this example, and let me say, when you solve this, you probably what do you think when you see this? You think, well, this 1 over n squared is going to go to 0, so this is going to be the square root of 4, right? That's really what you think. Your initial idea is that the limit of this thing, as n goes to infinity, really should be just the square root of the limit of this thing, right? You feel like I should just be able to put the limit inside here and take the limit of this thing, right? I should be able to slide the limit through the square root, right? And so the question is that okay? And the answer is yes, actually, sometimes. Yeah, the answer, so in this case, the answer is yes, right? It turned out to be the answer was 2. That was okay. there's a theorem that tells you when it is okay. Okay. If you have a sequence and you have a function like the square root, if a sub n converges to L and f is continuous at L, then the limit of f of a of n is f of the limit of a of n. And that is f of L. Okay, so this is the example, right? Here you have the sequence f. You have this sequence, right? The limit of this sequence is 4, right? And you have this function, f of x is the square root of x, right? Right? So the limit of the square root of this is the square root of the limit. Right? Is the square root of the limit. Okay. The limit of the square root of the sequence is the square root of the limit of the sequence. In other words, the square root of 4, which is 2. Okay. So as long as you've got a function that's continuous, you can slide the limit through. Okay. So for example, if I say, right, what's the limit as n goes to infinity of cosine pi over n? What's the answer? Say, I can slide it in. I'm going to get the cosine of 0, right? So that's 1. Right? You can slide the limit through and say, I'm going to take the limit of pi over n as n goes to infinity, that's 0. So I get cosine of 0. Okay. If I take the limit of the natural log of n over 1 plus n as n goes to infinity, right? Well, what's that?
0.
It's going to be 0, right? Because you take the limit inside here, you get 1. Natural log of 1 is 0. Okay, right? If I take the limit that's enough. Okay, right? So this is a pretty useful thing, right? You take limits of functions of things, you can slide the limit. Okay. Sorry, I think I didn't bring my phone today. What time is it? 12:30. 12:30. Okay, great. 10 more minutes. Okay. Okay. So here is another very useful theorem. Suppose you have a sequence, and you have a function such that f of n equals a sub n. Okay. So here's the picture, right? You have some sequence. Right? You have some sequence. A sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6. Right? but you also have a function, and the function takes on the same values at those times, right? So you have some function. Okay. So you have the function, and it agrees with your sequence. Okay. Then, if the function has a limit, if the limit of the function as x goes to infinity exists, then a sub n also goes to L. If the function converges to something, then the limit converges to something. Okay. So the above allows us to invoke L'Hopital's rule allows us sometimes to invoke L'Hopital's rule. Okay, so I hope you remember L'Hopital's rule. It says this, right? If the limit of f is 0 as x approaches infinity, and the limit of g is 0 as x approaches infinity, then the limit of f over g as x approaches infinity is the limit of f prime over g prime. Or the limit of f is plus or minus infinity, and the limit of g is plus or minus infinity. So even if you don't know L'Hopital's rule, that's okay. I'll show you how we're going to use it. Okay. So here's an example. Okay. Somebody gives you a sequence, natural log of n over n. Okay. Here it is. Here's your sequence, natural log of n over n. And you say, well, I'm going to make a function, natural log of x over x. Okay. Certainly, that function agrees with my sequence at every natural number, right? You make a function that agrees with your sequence at every point. Okay. Now, then the limit of the a sub n, as n goes to infinity, is the same thing as the limit of f of x as x goes to infinity. The limit of natural log of x over x as x goes to infinity. Okay, now, you look what happens to the top. As x goes to infinity, the top goes to infinity. As x goes to infinity, the bottom goes to infinity. So this is a case of L'Hopital's rule. The top goes to infinity, the bottom goes to infinity. So by L'Hopital's rule, this is the same thing as the limit of the derivative of the top over the derivative of the bottom. Okay, you got f over g. Both of them go to infinity. Then it's okay to take the derivative of the top over the derivative of the bottom and see what happens as that goes to infinity. Okay, so you differentiate the top, you get 1 over x. You differentiate the bottom, you get x. Right? And as x goes to infinity, this goes to 0. This goes to 0. And so that tells me that my original sequence goes to 0. Okay. Any questions? Any questions? Shichen, do you have a question? No? Okay, another example. The limit of n to the k over 2 to the n as n goes to infinity. Again, you make up some function, right? X to the k over 2 to the x, right? And you're going to take the limit of that guy as x goes to infinity, x to the k over 2 to the x. Okay. Again, you see what happens as x goes to infinity.